Today we need to cover a very, very important topic in AP Calculus, and that's functions. And last year we spent a lot of time on this in pre-calculus, and it's going to be very important to us. Remember our function family? Remember all of our family members that we said we didn't want to put them out on the deck at Thanksgiving dinner when it was snowing and cold. We wanted to keep everybody together as a family. Well, I'm not going to go through every one of those right now. We are actually going to eventually create a whole section in your binder for function families as we learn and grow about them. You know, we can start with linears, right? Linears. And every one of these, you should have a picture in your head of what the graph looks like. A linear looks like that. I may just throw up a quick little graph. We have quadratics, right, which look like this. We have cubics, which look like this. Now, let's stop for a minute. What is the domain and range of all three of these? Oh, that's right. Domain and range will continue to be important. What's the domain of all three of these? All, isn't it negative infinity to positive infinity? Yes. And isn't it the same thing? Now, how about the range? The range for this one, doesn't it depend upon where the vertex is? Yeah. Okay. So just keep those things in mind. Domain and range is not going away. How about absolute value? The V. That's right. Very good. The V. How about square root function? Yeah, the one that's like half, right? Somebody said, woo, and just kind of drew that half of the graph. That's good. And remember, the domain for this one would start right here at A, right? Whatever that number is. That's where the domain would start. How about this one? The reciprocal function. What am I talking about? I'm talking about one like this. F of x equals 1 over x. Isn't that this one that has two asymptotes to it? Right? And then, oh, that's right, we spent a bunch of time with some of our favorite friends at the end of the year, like some of our favorite family members, the exponential functions. We would never think of putting them out on the deck at Thanksgiving and eating their food in the cold. The exponential functions look like that. They take off exponentially. And then there's an inverse function for exponential functions, right? What is that? The log function. Very good. You people did not forget everything over the summer. Logarithmic. And of course, there can be the natural log, which is very similar. The logarithmic functions. All right. What is this? If it's a log function, what is this right here? That's 1. Very good. What is it if it's the natural log function? If it's the natural log function, this isn't 1, this is e, right? Because right. Let's see here. I paused the video for a second and realized that I made a mistake here. That this is not e. This is always 1, whether it's the natural log function or whether it's the regular log function. Sorry for that mistake. And then we also spent a lot of time with trig functions, right? We learned about ones like sine, which does this. And we learned about cosine, which does this. And we learned about tangent, which does this crazy thing. And it has asymptotes all over the place. Okay? And then we learned about where the hills and valleys meet, right? Secant and cosecant. Secant and cosecant. So we've learned, this is actually a pretty good list. I mean, I've went through a lot of them. You know, cosecant, remember you kind of draw the cosine graph, and then it meets the hills and valleys, so on. And then secant is very similar. So we have a huge family of functions, and there's still some that I haven't talked about. But we need to review what is a function, too. Okay? What is a function? Okay? Well, a function is that one-to-one. All right? Correspondence. Right? One-to-one correspondence. One-to-one. What do we mean by one-to-one correspondence? We mean each x, I'm just going to put it this way, each x is matched to exactly one y. All right? And we spent a good bit of time last year talking about, is this a function or is it not a function? Remember the vertical line test?
Yes.
Okay? The vertical line test says if this is situation A and this is situation B, which one is not a function? B is not a function because it fails the vertical line test. It hits the function in two places. Now, why does that mean it's not a function? Because it fails the definition I just said. This x right here, whatever this x value is, let's say that it's negative 2. If that's negative 2, and let's say that this value is negative 3, and this is positive 3, okay? Well, this negative 2 right here is matched to two different values. That's why that's a problem. Okay? So that is not a function. How about our old friend domain? Think of our old function machine, right? All the x, remember, right? All the x values that make the function work. All x values that work. All the ones that the function will not spit out. If it spits the number out, it's not in the domain. Okay? For example, I'll do an easy one. Let's say I had f of x equals 1 over x plus 7. This is an easy one. What is one number that function will spit out? Negative 7. If I put a negative 7 in right here, I get 1 over 0, which is a problem. Frowny face. So that means the domain of this one would be negative infinity to 7. We do not include the 7, union 7 to positive infinity. All right? And then range is all the y values that it spits out. Okay? And excuse me for my mistake, this should be a negative 7 there. Okay? Range is all the y values, of course, that it spits out. All right? And we usually have to consider this either from the graph, consider the graph, or the table on this one. All right, to figure out range, because we have to look at the y values. All right? Now, let's just keep in mind, I want you to keep in mind our function machine. because it is very important. Here's my simple de-dimple function machine. All right? You're putting in an x, you're spitting out a y. And that very simple concept is so important all the way through calculus. The idea of putting a number in, okay, if f of x equals 3x minus 7, and I want to find f of 2, let's say. Well, what am I doing? I'm putting a 2 into the function. Then the function is going to do something to the function, or to the number. It's going to do 3 times 2 minus 7, which is going to be negative 1, so it's going to spit out a negative 1. All right, and that sounds very basic, but it's a concept that shows up over and over and over again. Now, how about our old friends, even functions and odd functions? A function is even. Here's our old test. If f of x equals f of negative x. So if you remember, we would give you a function like, let's just do an example here. Let's say that f of x equals 3x minus 4. We'll just do a simple linear. We want to know, is that function even? Well, to know if it's even or not, I have to use this little test. I want to know if the function 3x minus 4 is equal to the function when I plug in a negative x. So I'm going to replace this x with a negative x, like that. If it is even, the left and the right side will be the same. So this is 3x minus 4. This is negative 3x minus 4. They ain't the same. So it's not even. We know that. We don't know if it's odd yet, but we know that it is not even. How do I know if a function is odd? I don't know if you remember that test. Then it's f of negative x equals negative 1 times the function. Or the opposite of the function. You just take a negative through, whichever way you want to think of it. So if I want to see if this function is odd, then I just complete the test. I already know what f of negative x is. F of negative x is this. So f of negative x is negative 3x minus 4. And then I want to check to see if negative 1 times the original function times 3x minus 4 is the same thing as that. It is negative 3x plus 4. They are not the same, so this function is neither. And that is possible, to have a function that is neither even nor odd. All right? And let's say a couple other things about this while we're on this page. Even functions are symmetric. The reason this works is they are symmetric about the y-axis. They have perfect symmetry about the y-axis. If I fold it on the y-axis, it will lay on top of the other side. The classic example, of course, is our old friend the quadratic. So long as the quadratic has a vertex, an x-coordinate of 0. Okay, that one is symmetric because it would lay, across the other side. If it is odd, it's symmetric about the origin. And remember, in this case, you flip it twice. Like a cubic. Okay? A cubic is symmetric about the origin. I'm out of room on this page, but a cubic, if I fold it twice, fold it here, and then fold it down, it lays exactly on top of it. All right? Now, so you're going to be asked some to find out if a function is even, odd, or neither, and I've shown you a couple examples for that. But we need to refresh our memories also about our old family member that a lot of you wanted to boot out on Thanksgiving Day, which I didn't think was fair. Piecewise functions. Piecewise functions will not go away this year. They will continue to keep showing up at the family dinner. So we're going to have to keep feeding them. We need to love them just like everybody else. Let's just look at an example of one. Let's graph this piecewise function. Negative x for x less than 0, x squared for 0 is less than or equal to x is less than or equal to 1, and it's 1 for x greater than 1. So let's see how to graph this thing. Well, we have to graph it in pieces. Okay? So I'm going to make a graph, and I'm going to start with the first piece being this one. It says that it's just a regular linear function going through 0, but it has a slope of negative 1. Okay, so let's think of what that looks like. Isn't that, and it's supposed to go through 0, right? Isn't that it? But it's only this function when x is less than 0, right? So I need to mark out something. That doesn't exist. And it says it's when it's less than 0, which means this little deal right here should be an open circle. Open circle right there. All right? So there's our first piece. Then it says it is the function x squared in between 0 and 1. Well, that's a quadratic, right? So here's 1. I'm going to make this kind of bigger so we can see what the heck we're doing. From 0 to 1, it is a quadratic, so I will use a different color. I've been thinking about Christmas lately, so I will make the green match the red. Now, it says that it is that these are both less than or equal to's. So I need to color in this dot, and I need to color in this dot. All right? And let's do our last piece, which is this one. It says that it is the function 1. Isn't that a constant function? Which means it's a horizontal line. So from 1 on, it is going to be a horizontal line, just like that, forevermore. Well, it says it's when it's, this one's kind of, it's a good question. What do we do with this circle? Well, it was colored in for this part right here, but it's technically like open for that part. You don't need to do that. Okay, just leave it colored in. If that ever works out that way to where they're the same point, just leave it colored in. So, the other thing that they might do is they might give you the function in a graph and say, write the function. I don't remember if we did them this way or not last year. Let's just see. Basically what we're doing is working backwards. That's the way Mater always liked to drive anyway, was backwards. And then this one comes up to here. You know, this point is 2, 1. This point is 1, 1, so on. So they've given you a piecewise function graphically. Now they want you to write the function. Okay? Well, it's really not, don't I just have two linears? Well, I need to figure out what the two linears are. All right? I know that my function is going to be piecewise and it's going to be split up into two parts. It looks to me like the first part is when x is greater than or equal to 0 but less than 1. And it looks like the next part is when x is in between 1 and 2, like that. So there's my two pieces. Now we need to figure out what the functions are. Well, it looks like to me, like this part right here, isn't that just y equals x? So this one is x. That's not that bad. The next one, we need to think of where does it intersect the y-axis? Well, it's going to come down here, and it's going to intersect at -1, isn't it? So isn't this one x minus 1? Right? So this function is x minus 1. You're just thinking backwards. Now, I'm not going to spend a lot of time on transformations because we should be good at that, but I just want to tell you that it might show up in your assignment tonight. Transformations. What do I mean by transformations? I mean, if I have the square root of x, what do I do to it to graph the square root of x minus 4? Without even looking at my graphing calculator. What's the transformation? Isn't it moved to the right 4? Here's the parent function, the square root of x. The transformation is that it's moved 4 units to the right, like that. There's the square root of x minus 4. So we learned a lot about those last year. Those are going to show up a little bit in homework, I think. Lastly, composite functions. Kind of touching on a lot of things, but like I told you, we can't spend 3 months to review pre-calculus when we've already learned it. What do I mean about a composite function? I mean one like this. F of x is x plus 7, and g of x is x squared minus 5. And then maybe they say, for example, find f of g of x. Isn't it also written another way sometimes? Isn't it sometimes like f dot g like that? Doesn't that mean the same thing? So that means we're going to plug g in for x. So the way f of g of x would look is I would have x squared minus 5 right here, and then I would have a plus 7. And then simplify it a little bit, it would be x squared plus 2. What if they wanted you to find f of g of negative 3? Well, wouldn't you do what I just did and then plug in negative 3? Right? So I would put in a negative 3 right here. So that would be 11. All right? And we are going to stop there for today.